now, welcome back to KhemWithKess. This is a recap of everything we learned for hydrohalogenation. I promise it's not going to be as bad for the rest of them. Just hang in there with me. So we've been doing a lot of problems with HX, and HX would be using if we had like a BR or a CL. But there are times that we may need to add HI to the problem. Do not be dismayed because the NaI, H2SO4, or again, changing some of the acids or the cations that are connected to the iodine, this would be the way that we would add HI. So you will see it in somewhat of this format because iodine and even fluorine are very reactive. So they need a little bit of different conditions in order to force things to happen. But our BR and CL are normally the trusted ones. When it's symmetrical, we stated we're always, for any of the problems, we're going to act as if the alkene is not there. We would notice that both of these carbons would be secondary, which would allow the BR to add to either one, the top or the bottom carbon. And of course, even though I didn't draw the hydrogen in, the hydrogen would be there. So use your imagination. When it's unsymmetrical, this is when we started talking about Mark's rule. Markovnikov's rule states that, again, if I see an unsymmetrical alkene, again, acting as if the double bond wasn't there, the top would be tertiary, the bottom would be secondary. The Cl would gravitate towards, of course, the tertiary because that's more stable, making it the major product, as the other structure would be secondary and minor. When it comes to the 1,2 hydride shift, we stated that it's important to actually look at the neighboring carbons to the double bond. So once we pretend these two carbons weren't connected to a double bond, the first one here is primary, the second one is secondary, but this is where we need to train our eye to look one more over to see that that was tertiary with a hydrogen on that carbon, causing us to get three products: a minor adding on the end, a major adding at the secondary location, and then the this one's not as major, so oops, sorry, let's just go ahead and switch that up real quick. That one is also minor because the 1,2 hydride takes precedence since it is tertiary. With the 1,2 methyl shift, we stated that, again, go back to the mechanisms if you have some questions. We stated that same idea. If we acted as if the double bond wasn't here, we would categorize it. And we see that right next to the double bond, anytime we have a quaternary carbon with a methyl on it, this would lead to a methyl shift. So here are your minor products for the locations of where the double bond is, so here and here, and then a methyl shift would cause the methyl to shift to the more stable intermediate from the previous problem and causing a shift of the methyl group, allowing the Cl to add to the more stable. And a 1,2 ring expansion, I know it's going to take some practice. Again, we focus on the main two carbons, and those would be our two answers that we see. And then with the ring expansion, when we go back to the mechanism, we recognize how the ring expansion occurs. That would give us the final product. So only in cases of hydrohalogenation do you need to think about all of these 5 methods. And again, I cannot stress it enough. Every mechanism is important. So I would suggest that you practice each one of these mechanisms 2 to 3 times for a better understanding. Let me know if this helps.